In this mini lecture, we'll discuss light as energy and introduce the particle-like properties of light. We'll start off by discussing a classic experiment. Here we have an evacuated tube, which means there's no gas molecules inside the tube, with a piece of metal on one side and a metal positive terminal on the other side. This device is connected to a voltage source and a current meter so that any changes to the flow of electric current can be monitored. The surface of the metal is irradiated with light, which causes electrons to be emitted from the metal surface. This happens because the energy of the light is absorbed by the electrons in the metal atoms, and if enough energy is provided, the electrons become so excited that they are ejected from the metal atom into the empty space inside the evacuated chamber. Then they are pulled by their attraction to this positive terminal on the other side of the tube, and they flow through the circuit. This leads to a rise in the current detected by the current meter. So with this setup, we can shine light of different frequencies at the metal surface and see at which point electrons begin to be ejected by watching for the current to spike. Now this chart shows some data from that setup, and it shows the frequency of light that is aimed at the metal surface on the x-axis and the rate of electron ejection on the y-axis. And remember, the rate of electron ejection is being detected by changes in current. So you can also think of the y-axis as the current being detected by the device on the last slide. Now note that at low frequencies, there is a very low rate of electron ejection, and that this rate does not change as we steadily increase the frequency of the light, moving from left to right on the x-axis. However, at a very specific frequency, we suddenly see a spike in the rate of electron ejection, almost as if we've suddenly turned on the emission of the electrons from the surface of the metal. This point at which the electrons begin to be ejected is called the threshold frequency, and it indicates the minimum frequency of light that is needed to eject electrons from the metal atoms. Now, curiously, as the frequency of the light continues to increase along the x-axis, the rate of electron ejection remains constant. So it appears as though once you reach a certain frequency, the same number of electrons will be ejected no matter how much higher you go in frequency. Now, Einstein and other scientists viewing these results had hypothesized that the frequency of light was directly correlated to the energy of the light. So as the frequency increases on the x-axis here, the energy of the light is increasing. So it made sense to them that if the electrons in the metal atoms required a certain amount of energy to be ejected, that ejection would turn on at a specific frequency, the threshold frequency, when the energy provided by the light matched the energy needed to eject an electron. However, they also expected that continuing to increase the frequency or energy of the light should also cause more electrons to be ejected, because if we're providing more energy to the metal atoms at these higher frequencies, then shouldn't we see more electrons being ejected as there's more energy provided to eject those electrons? However, that is not confirmed by this data, as the rate of electron ejection stays constant after this threshold frequency. They also hypothesized that if low frequency light wasn't able to provide enough energy at first, that maybe exposing the metal to lower frequency light for a long period of time may eventually build up enough energy in the metal to lead to electron ejection. But this also was not the case, and no lag time was witnessed when reaching the threshold frequency needed to eject electrons. Ejection just happened instantaneously, so there was no evidence to support a buildup of energy needed to eject an electron. So they then tried changing the intensity of the light, which should also increase the energy provided by the light. They expected that this time, if the higher intensity light carried more energy, that electron ejection might begin at a lower frequency. But oddly enough, they saw that the same threshold frequency was still needed to eject electrons, as we can see by the fact that both the red and the blue curves here are spiking at the same frequency. But they did notice that this higher intensity light did yield a higher rate of ejection of electrons after the threshold frequency due to the increased energy of the higher intensity light, which is why we see the blue curve here higher on the y-axis than the red curve. So what's going on here? Einstein's conclusion from all of this is that light energy must come in packets of a specific amount of energy, which he dubbed photons, and that energy of these photons depends on the frequency of the light. So let's take a moment to think about why this explains the data. If the light delivers energy in packets, or photons, that are dependent on the frequency, and each photon is only able to excite one electron, and also can't be combined with another photon in order to increase the amount of energy that's being delivered, then it makes sense that as the frequency of the light increases, the energy of the photons increases until we reach this required energy needed to inject an electron, or the threshold frequency. And then each photon that hits the metal surface has enough energy to eject just one electron. So if we then continue to increase the frequency or increase the amount of energy in each photon, we don't see additional electrons being ejected because each photon can only excite one electron at a time. But the extra energy will still be transferred to the electron, so once it's ejected, that extra energy will manifest itself as the speed at which the electron is moving through space. So something we can't tell from this data, and that they couldn't tell at the time, was that once the electrons begin to be ejected from the metal atoms, once we reach this threshold frequency, then the velocities of those electrons are what is steadily increasing as the frequency continues to increase. And we can't see that on this graph because this is just monitoring the number of photons, not the speed at which those photons are moving. Additionally, these packets of energy, or photons, also explain why we see more electrons ejected with higher intensity light. Intensity indicates the number of photons that are hitting the surface of the metal at one time. So as the intensity of the light is increased, the number of photons striking the surface is increased. So each of those photons still needs to contain enough energy to eject an electron, which is why the threshold frequency for the higher intensity light is the same as the lower intensity light. But since there are more of those photons hitting the surface of the metal at one time, then there are more electrons being ejected. And this is why we see this blue curve appearing at a higher point on the y-axis than we do the red curve. Now the equation below, or over here on the right, shows that the energy of a photon can be determined by multiplying the frequency of the photon by h, which is Planck's constant given below. And since we know from the previous mini lecture that frequency is equal to the speed of light divided by the wavelength, then we can also write that the energy of the photon will equal h times c over lambda. So anytime you see h nu, just remember you can also swap that out for hc over lambda. And we're going to see on the next few slides with these equations that, you want to remember that those two things are interchangeable. And this is important because if you're provided frequency, you want to use h nu to solve for energy. But if you're given wavelength, you can use hc over wavelength to solve for the energy. It's important to note that frequency and energy have a positive correlation. So as frequency increases, so does the energy. But wavelength and energy are inversely correlated. So as wavelength increases or gets longer, the energy decreases. And as wavelength decreases or gets shorter, the energy increases. So going back to some colors of the visible spectrum, we saw that blue light has a shorter wavelength than red light. So this also means that blue light is a higher energy than red light. This is one of the reasons why red light is used in photographic darkrooms, as it doesn't have enough energy to react with the chemicals used in creating and developing photos. The experiment we described a few slides back utilized what is now known as the photoelectric effect, where light of a certain frequency can eject electrons from the surface of a metal. The electrons that are ejected in this type of experiment are sometimes called photoelectrons, since they are created by photons striking the surface of the metal and exciting the electron. As we saw, the photons that hit the surface need to have enough energy to eject the electrons, and the energy required will be dependent on the type of metal, and it's going to be referred to as the binding energy, or sometimes also called the work function. This is given the symbol phi. So to determine the threshold frequency needed by the metal electrons, we can set the energy of the light, h nu, equal to the binding energy or work function. In this way, if the binding energy is known, we can solve for the threshold frequency. Or if the threshold frequency is known, we can solve for the binding energy. It is really important, though, to note that this equation will not apply to every situation, but is very specific to the conditions that occur when an electron is ejected with no excess energy, therefore no velocity. So this equation is only to be used when the energy of the light perfectly matches the binding energy of the metal electron. And this will always be the case when we're at the threshold frequency, so that's when you want to use this equation. In the situation where the photon's energy is greater than the binding energy, then the electrons will have some leftover energy after being excited. This energy will manifest itself as kinetic energy and give the electron a specific velocity. In this equation, we have excess energy, or the kinetic energy of the electron, on the left, and the energy of the light, h nu, minus the binding energy on the right. Note that the energy of the light, h nu, needs to be greater than the binding energy in order for there to be some excess energy left over. So this is why we're subtracting the binding energy specifically from the energy of the light. Also note that this equation becomes the first equation on the left when we set the kinetic energy equal to 0, as this would indicate the situation where there wouldn't be any leftover energy, as the energy of the light, h nu, would perfectly match the binding energy, and therefore subtracting the two would yield 0 for the excess energy, or kinetic energy. From this kinetic energy, we can use the physics definition for kinetic energy, 1/2 mv squared, to determine the velocity of the electron. And remember, be really careful here about these two symbols because they do represent different values. V is velocity, but nu represents the frequency. Note that mass in this equation will be the mass of an electron, which is a constant that will be provided on the equation sheet for quizzes and exams. Now, at the bottom of this slide, we see several different wavelengths of light directed at a metal surface, and in the case of the red light, no electrons are ejected because the photons do not have enough energy. For the green light, the photons have enough energy to eject electrons and enough leftover energy to give a velocity for the electrons of 2.96 times 10 to the 5th meters per second. In the case of the violet light, which has a shorter wavelength and therefore even more energy, now the energy of the photons is even greater, so electrons are now ejected with an even faster velocity because there's more leftover energy. So this velocity is now 6.22 times 10 to the 5th meters per second. Now, from all the information provided in this graphic, you can actually determine the binding energy of the metal using the equations above as about 3.2 times 10 to the 19th. So I challenge you to see if you can use the equations above and the information that's provided on the diagram here to solve for this number for the binding energy and see if you can do that yourself. The discovery of the photoelectric effect represented a significant advancement in how light was understood because it connected the wave-like properties of light to particle-like properties and set up an interesting phenomenon called wave-particle duality, which is also displayed by electrons. So the answer to whether light is a particle or a wave is that it is actually both. The energy transmitted by light is dictated by the wave-like properties and therefore can take any value for frequency or wavelength and provide a continuous spectrum of energy possibilities. But since that energy must also be transmitted in packets that each contain a specific amount of energy, therefore, the energy is delivered in quantized bits with very discrete values, rather than a continuous spectrum of energy. This concludes the second mini lecture for Chapter 4. Please note any questions you may have about this material and how it is utilized to solve problems in the sapling homework or end of chapter exercises for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our virtual class meetings, and during that time we will focus more on problem solving for concepts in this chapter.